Thanks for joining. My name is Christof Klein. I'm the Chief Service Officer at IMS Nanofabrication, and I'm responsible for global service and support. Today, I want to talk about the versatility of MBMW multi-beam mask writers. Multi-beam mask writers have been around for quite some time by now. It was almost 10 years ago that we shipped our first beta tours to customers. I remember this time quite vividly. It was very painful at first, but we made it work. And now multi-beam mask writers are the standard tools for printing EUV masks. So we made quite some progress since then. And today I would like to convince you of the versatility of multi-beam mask writers. And by showing you that they're not limited to one technology node only. Every tool in our portfolio can cover actually a relatively wide range of technology nodes. First and foremost, our MBMW 100 Flex, which was designed to cover the mature technology nodes up to 45 nanometers and go down to 10 nanometers, and with the EUV extension package, even to the 7 nano technology node. But also our leading edge tools, the standard workhorse, that's our most sold tool so far, the MBMW 201 or 261, which covers a range from 10 down to 3 nanometer technology node. And the leading edge tool that's currently in production at our customers is our MBMW 301 tool, which covers a range from 5 nanometers down to 14A. And what we're releasing this year is the next generation. It's our 401 tool generation. This one is an extension of the 301 technology and goes down to even the 7 angstrom node. All of these mask writers have one thing in common. They're very versatile, and they can cover a range that's even wider than what's depicted here. It can be extended to the left and to the right based on customer needs. So we're happy to discuss with our customers about their specific use case and how to make that happen and how to best support them. So today I would like to convince you that the tours, the MBMW tours, are really extremely valuable and versatile, and that they should be present in every advanced mask shop. But before I go into this, let's take a step back. Why do we need multi-beam in the first place? And this is connected to the technology roadmap. So as the nodes went down from 500 nanometers to the left to the angstrom nodes on the very right, different lithography tools were used to make that happen. This was driven by the human desire to miniaturize in order to maximize cost efficiency and performance. And the nodes on the left-hand side, down to about 100 nanometers, were covered by the UV scanners, replaced by the DUV scanners covering the range in the middle. And on the right-hand side, at this particular this particular point, you can see the introduction of EUV, the EUV technology, which brought the curve down again. And interestingly enough, all these lithography technology generations are tied to a certain eBeam mask writing generation, with the EUV being covered by Gaussian beam writers, DUV tools covered by variable shape beam writers, and the EUV technology enabled finally by multi-beam mask writers. But multi-beam can be used for more than just the most advanced leading edge nodes or for EUV. They can be extended into the DUV tools up to around 45 nanometers. And theoretically, they can be used also for less advanced nodes, but then other technologies are more cost effective. And as a matter of fact, when you look at the situation today, almost all technology nodes can be, by one way or another, realized by multi-beam mask writers. On the left-hand side, we can see the multi-beam laser writers that cover a range from 350 nanometers down to 90 nanometers, roughly. And on the right-hand side, you have the multi-beam eBeam mask writers that cover the range from 45 nanometers down to the angstrom area. In between, we have a narrow gap where VSB still has its advantages. So in this range, at the moment, VSB is definitely the most cost-effective solution. Now looking at the multi-beam mask writers that we have in our portfolio, again, we're covering the full range from 45 nanometers down to 7A. And today, again, I want to talk about the versatility of our products. I would like to start with the 100 Flex tool, which was per design a very flexible tool that covers a wide range of technology nodes from 45 nanometers down to the 7 nanometer technology node. And what makes this tool so flexible or versatile? Well, this is enabled by a series of configurations that are optimized for a certain technology node. For example, in configuration A, the tool is optimized for technology nodes from 45 nanometers down to 32 nanometers. In this setting, it achieves a write time of less than 3 hours for a mask. The exact write time depends, of course, on the process that's being used by our customers, or to be more precise, mainly it depends on the resist sensitivity. Likewise, in configuration B, the tool is optimized for technology nodes between 28 nanometers down to 22 nanometers at a write time of less than 4 hours. And for configuration C, we can cover quite advanced nodes, 14 nanometer down to 10 nanometer at a write time of less than 6 hours. And I mentioned the EUV extension package already earlier. This enables the tool to expose EUV masks for the 7 nanometer node at about 12 hours write time. Okay, that's the theory. And now let's look into the data. This is data from one of our customers where we compared actual write times that were recorded on our mask writers with the write time of the POR tool for this particular technology node, which was always a VSB tool. So looking into write mode A, for that we used 32 nanometer technology patterns to do this comparison. And you can see that for the multi-beam tool, all the write times are the same. They were 3 hours, as mentioned earlier, independent of the complexity of the layout. And that's one of the key features of multi-beam. It always writes for the same time, and it does not depend on the complexity of a given structure. For VSB, complexity has a significant impact, and you can see that for the contact layer, which is the least complex, the write time advantage of the Flex tool is about 3x. For poly, it's 4x, and for metal, it's even 5x in this particular use case. When we look at the more advanced write mode C of the Flex tool, which enables designs or a technology node down to 10 nanometers at a write time of about 6 hours or less than 6 hours, we see that the actual write time really was below 6 hours, again, independent of pattern complexity. For contacts, when comparing it to the POR mask writer, which again was a VSB tool, the most advanced VSB tool in that case. For contacts, the write time was almost the same, only slightly faster. But for poly, the advantage was again 2x, and for metal, it was 3x. So over a quite wide range of technology nodes, we really see significant throughput improvements relative to the state-of-the-art or POR mask writers that are being used in the factories, which are always VSP tools. So this really shows the cost of ownership advantage that the flex tool can provide, and also the versatility of the application range of this particular tool. And in order to address concerns that people might have regarding tool matching, is it possible to replace the VSP tool with a multi-beam tool, in this case, MBMW 100 Flex? And the answer is yes, you can do it seamlessly when you do apply the matching function that's provided with the Flex tool. What you can see here on the left is the picture, a SEM picture of a certain structure that's realized on the MBMW 100 Flex without the matching function on. You see high pattern fidelity relative to the original design, which is a little bit blurred out in the VSP case, where the tool blur or the beam blur is simply higher due to the technology limitations. And this can be matched really well when switching the matching function on, as shown on the right-hand side, leading to one-to-one comparability of these two tools. So the Flex tool can really replace the VSP tool in the production flow. When switching the beam matching function on, you see no difference in the end result, but you still benefit from the high throughput, from the throughput gain. But what can the Flex tool ultimately do when set up in write mode C? Let's look at the litho specs that were achieved. We achieved 0.9 nanometers 3 sigma for local CDU, which is well within spec. 1 nanometer 3 sigma for local and global registration, also in spec. And we achieved also quite high resolution, down to 24 nanometers, both for isolated lines and isolated spaces. For dense structures, in the demonstration, we achieved 32 nanometers half pitch on this special test structure that IMS usually uses to check any angle structures and half pitch resolution limits. We call it the chevron pattern, which was well resolved down to 32 nanometers half pitch. So all in all, this is pretty good for a mature node tool, which comes at a relatively good price. So I really encourage advanced mask shops to look into this in more detail. Looking into the MBMW 301 and the flexibility of this tool, also this tool has a variety of settings and write modes that can be applied, making it very versatile. What's the difference here relative to the 201 generation and the Flex tools? It's a much higher number of beams. It's more than 2x more than what we have in the previous tool generations. It's almost 600,000 beams at a maximum beam current of 2.8 microamps, a data rate of 450 gigabit per second. Per default, it comes with two beam sizes, 11 nanometers and 15. And this allows a minimum pixel size of 2.2 nanometers at 720 dose levels. And you can see here 3 different write modes and the comparison to the performance of an MBMW 261, which is the previous generation tool. And when looking at the same write quality, so write mode 5, which is designed for 5 nanometers down to 3 nanometers, when it comes to technology node, we see a 2x improvement in write time. Same for write mode 3, which was designed for 3 nanometers and 2 nanometers. And for the write mode 2, which is the most precise write mode, which gives the best litho performance. Also here, we see a 2x productivity boost of the 301 tool generation relatively to 261. So also this covers a relatively wide range of technology nodes and at not only at improved write time, but also at improved litho performance. This is customer data taken from customer production data, actually. So that's also why the exact numbers were removed. But we're looking at the relative improvement here, and we can see that for 301, the local CDU improved by 20% relative to the 201 generation, and the average to target improved by 20%, same as the global CDU, which also improved by 20%. And it also came with a new correction that improved global CDU further by 50%. You can see that by the width of the distribution here, which goes down from this to that width. So all of that looks pretty good with overall 20% improvement. And we're now adding a new Z-height correction to the mix, which improves the performance even further. It corrects for placement errors that are introduced by Z-height variations across the mask. These Z-height variations are unavoidable, mainly due to mask sag and maybe some imperfections in the alignment. So when you have these kind of variations, you always see a linear response to them. And in an experiment, we artificially introduced a variation of plus minus 1 micron in Z height. And without this correction, you can really see a linear response of the 3 sigma value relative to the displacement. And same for X and for Y. And with the function on, this effect can be eliminated almost completely. You only see some residual noise. And the end result that can be achieved here is also quite good. We can get down to 0.24 nanometers 3 sigma in X and 0.27 nanometer in Y in this particular test case. So again, this new correction will be released for all MBMW 301 tools and is available as an upgrade option for the 201 and 261 tools as well. So let's now move on to the latest generation of our fleet. We just released the MBMW 401 tour, which was first presented at Bacchus last year. And the 401 tool provides versatility beyond the leading edge. It really allows you to go down to 7A technology to do R&D for this technology node that's quite a bit in the future. But it gives you the ability to do all your R&D work and your testing down to this technology node if you want to. At the same time, you can print 5 nanometer technology masks in less than 5 hours. Comes with automated beam size switching with 4 different beam sizes, and in the end gives significant cost of ownership advantage relative to the previous tool generations. The key features are shown on this slide. Here we compare the MBMW 301 with the MBMW 401 tool generation. The current is increased by 25%, up to 3.5 microamps. The data rate is improved by 50%. Beam size options increased by 2x to 4. And the mask write time is reduced by up to 30% relative to the 301 tool generation. It also comes with an improved anti-fogging kit and a reduced minimum pixel size. So when we look at the performance of the 401 tool generation relative to the 301 tool generation, we see either a 30% improvement in throughput when we run the tools at the same write quality as shown on the top left, or we see an improvement of about 20% with respect to all litho specs when printing at the same speed. And on top of that, and that relates to the R&D work that can be done using our 401 tool, we have the MBMW 401 Ultra write mode, which is a bit slower, but can provide up to 40% improvement when it comes to registration and pattern fidelity. Now let's look at some data, some print results. So all of the data that I'm showing now was realized on the new IMS demo tool that's running in high precision mode in this case. We set this tool up in a new chamber, which is a customer equivalent chamber with a temperature stability that's similar to what we have available in the fabs, and also the same quality of magnetic shielding. So this, for the first time, allows us to also look at the global patterns in a meaningful way at IMS, which we're not able to do prior. And the results I'm showing here are local CDU results. We achieved about 0.3 nanometers, 3 sigma local CDU. When looking at the global scale, same pattern, 110 nanometer lines, we achieved 0.36 nanometers 3 sigma. And now moving on to placement, local reg, we were able to expose patterns with a 3 sigma value of about 0.39 nanometers 3 sigma locally, and a global reg of 0.65. Here, we still see some room for improvement that we're currently working on because there's some systematic signatures visible on the left-hand side, but this is work in progress. And now moving on to some SEM images, because these are part of every litho demonstration. So we were able to demonstrate 19 nanometer lines and spaces resolution using our chevron pattern at both 50% pattern density and 0% background. Okay, and with that, I want to summarize. So hopefully I was able to convince you that the multi-beam mask writers that we're providing are really very versatile. They cover a wide range of technology nodes, especially when looking at the flex tool, which can go from the mature nodes down to EUV. And the leading edge tools can go even beyond of what's currently needed, which might be very interesting for our leading edge customers who will do R&D work for these technology nodes very soon. So our tools are really very versatile, and they can be seen as the Swiss Army knives of the most advanced mask writers. And with that, I want to thank you for joining and your attention, and want to wish you a good day. Thank you.